all right, at the point P. And all the conjugate variable derivatives are 0, all right, then f is a differentiable of P. Because really what I'd like to claim is that the conjugate variable derivatives vanishing is equivalent to the Cauchy-Riemann equations. What I'm telling you is that these guys right here, this business right here, is equivalent to the ACR equations. It's really the same set of equations, just recast in a different notation. Let's look at the proof of that. It relies, the reason I had to do the last theorem, well, there's a couple of different reasons. One, I think it's healthy for you to see what I know about different ways of characterizing a differentiability, because they all matter at various points in the story, you know?
Yeah.
But more specifically here, I have to use the previous theorem to prove this one. And so, check this out. So what is partial f, partial zeta bar j? So what was the definition? Partial zeta bar j is over here, right?
Yeah.
So it is 1/2 partial f partial x1, right? Minus 1/2 Vj inverse, right? Partial f partial xj. So I just added
an f.
I just fed f to this differential operator.
Yeah.
Now, if the Cauchy-Riemann equations hold,
That should equal 0.
that should be 0.
Yeah.
If the Cauchy-Riemann equations hold, then remember what this is? This is, we can trade differentiation with respect to xj for multiplication by
Oh,
bj.
so yeah, it'd be bk or bj.
Mhm. So this is 1/2 partial f partial x1 minus 1/2 Vj inverse partial f partial x1, times Vj. There probably should be a multiplication here. Since I'm writing multiplication symbols, whatever. Now, and this is where I had to assume commutative. Because I need the commutativity in order to
Flip them
flip
around.
them, and when I flip them, then I get Vj inverse,
Yep, cancels.
1/2 minus 1/2,
Oh, yeah.
0. So if the Cauchy-Riemann equations hold, then conjugate variables vanish. Derivative is 0. Conversely, right? Conversely, suppose that this was 0. Right, can I erase this calculation?
Yeah, I can write the
I'll
calculation.
tell you, I'll leave the
myself.
calculation and I'll just write it below it. 1/2. Suppose we had 1/2 partial x1 minus 1/2 Vj inverse times partial f partial xj. Suppose that this is given to be 0. My claim is that that is just a different way of writing the Cauchy-Riemann equations. Solve it. Solve it for partial f x1.
Well, you can just put the b.
Oh, yeah.
Bj and then 1/2
Yes,
1/2.
Right, so partial f partial xj. So move the other side, right?
Yeah.
Is partial f partial x1. It always involves that commuting aspect of it. So that's fine. Vj inverse times that is partial f partial x1, which then says that partial f partial xj is equal to Vj times partial f partial x1, which of course I often like to write I mean, this is kind of just a matter of style, but I often like to write it like this. But, you know, anyway, the point is, these are the ACR equations. So the vanishing of these conjugate variables is entirely equivalent to imposing the Cauchy-Riemann equations.
Yeah, because you've proven that you could flop them, or the BK is equal to partial F partial XK. Yeah, that allows you to say, well, these are the Cauchy-Riemanns, and this way you can express it only by saying, only by this stuff, this theorem.
Right. Now,
so you're equating this, that if that theorem holds, then you have the Cauchy-Riemanns.
if this condition holds, this can, like, vanishing of the all n minus 1 conjugate derivatives is equivalent to the Cauchy-Riemann equations holding. So with the backdrop of knowing that the function's already real differentiable, we get a differentiability from either the Cauchy-Riemann equations holding, from right alinearity of the differential, from, you know, items 1, 2, or 3. Well, 2 was the. So you could justifiably call any of these things the Cauchy-Riemann equations. I mean, I wouldn't call right alinearity Cauchy-Riemann equations just as matter style, but like, I wouldn't be bothered if somebody said, oh, those are the Cauchy-Riemann equations, because they are.
Yeah.
But, you know, syntactically, are they really it? I don't know. Maybe these are really it.
Well,
but then,
I would say that because if you get to that point, then you can derive.
Right. But some people would insist on calling, I mean, these kind of simple-minded folks, I suppose, but other people might say, well, when I think of Cauchy-Riemann equations, I'm thinking of at like the component level. Because remember, F has like U1, U2, all the way out through UN, and it has n real component functions. And so I say that there are n minus 1 Cauchy-Riemann equations, but at the level of scalar equations, there are n times n minus 1. They're n squared minus n scalar equations. So for like for a 3-dimensional algebra, there's 6 Cauchy-Riemann equations. For a 4-dimensional algebra, there's
16.
16 minus 4, 12.
Oh yeah.
I mean, but yeah, this is, now, there's something called the Wertinger calculus, all right? And so what this is really what we're generalizing here. The Wertinger calculus is probably mispronouncing, but essentially you can look at, I'll just say this, Audrey, you can look at a function of 2 variables as a function of, like, say, x and y, right? Or you could look at it as a function of z and z bar. So here you're treating z and z bar as independent variables, all right? And so really what this use of z and z bar is it's really just a clever notation. It's a complex notation for having a function of 2 real variables. That's what it really is. It's a complex notation for function of 2 real variables. And so, for example, you can write stuff like df is partial f partial z dz plus partial f partial z bar dz bar. So in this wild world of Wertinger calculus, the complex differentiable functions, right? Those are the ones, the special functions on the plane, which have partial f partial z bar equal to 0.
Which would only, that means the f would just be equal to partial f partial z.
Yes. And you can also talk about, those are also called holomorphic functions. There's also something called an anti-holomorphic function. Anti-holomorphic function has
dz,
partial f partial z equal to 0, and it just has this piece.
I've never heard of that term, so.
Yeah, it's understandable.
Yeah.
And, but my point is, because you're not just limiting your universe of discourse to just complex differential functions, it's not really, it's a sneaky hybridization of some mathematics. I mean, the z bar notation.
Yeah.
It's a little bit, how do your generation say, sketch? No, so, it's not wrong, it's just gotta be careful not to read things into it that aren't there. And what I'm doing is setting up the same dangerous kind of notation for the algebra. See, because you can think about a function of variables x1 through xn versus a function of zeta bar 1, all the way up through zeta bar n. See, I could think about a function of n real variables, or I could think about a function of n algebra variables. And there again, I could give meaning to, df having like partial f partial zeta d zeta, partial f partial zeta. Now this is something I have not looked deeply into yet, by the way. Zeta bar 1, in terms of like what are the constants. I mean, I have some of this at the end of the paper. And then, so like for a differentiable function, all of these are 0, so your differential just has the zeta piece. Yeah. All right.
But in the fx, you would have every piece.
Right, but for an arbitrary real function,
that's true. That holds.
Of your algebra,
yeah,
you have those other pieces. And the thing is, you can still take you can take any function that's real differentiable, and you can calculate derivatives with respect to the algebra variable. You can calculate partial derivatives with respect to the algebra variable and all the conjugate variables. It's just, it's not a derivative with respect to the algebra unless you have all those conjugate variables vanishing, because only in that case do you actually have
to worry about them,
the genuine
a-differentiable
function. However, as you look at my paper, I have theorems that say basically what you'd like, which is that for these partial derivatives with respect to the algebra variables, you have the usual linearity product.
Yeah.
Nice stuff. So if you were working on a problem where you wanted to like look at the totality of all the differentiable functions, real variable functions, and then say something specific that happens for, a differentiable functions, this might be a useful universe of notation to use. I mean, that's. Anyway. So now I have I've told you pretty much the can you look at example 610 with me? I don't want to write it out.
Yeah.
So
we got direct sums of the reals. This is a hyperbolic. Yeah.
Yeah. This is H3.
Mm-hmm.
The 3 hyperbolic, and there you've got 2 conjugate variables, right? C.
Yep. Minus
with the jy or minus with the j squared c.
Mm-hmm.
1 j squared is an invertible basis, so we can step.
I thought no, that's right. If for every dimension you go up, you get another conjugate, right? So like if you're on 2, you get 1. If you're on 3, you get 2. Okay.
Yeah, I decided to number them so that I had the conjugate start at 2.
I thought we were missing a conjugate for some reason, but no,
you're fine. It's just and so I'm actually just fleshing out the the formulas I derived heuristically in general for you, in putting them into practice here. And so in this case, 3 minus n over 2, let's see, what is n here? N is equal to 3, right? So
Yeah.
quirky business, there is no partial x1 piece with partial zeta.
Yeah, because of the constant.
But you just get the 1/2, v2 inverse plus 1/2 v3 inverse. Now v2 is j.
Yeah.
J's inverse is j squared.
Squared.
J squared is v3 and its inverse is j.
Yeah.
So that's why we have partial zeta is 1.
Is j partial y plus j squared partial z.
That's alright.
Partial zeta, and then
What?
partial x1.
Oh. Sorry, I feel like I got that twisted. Just a second here. I'm seeing that the j and the j squared should be flippy floppy there.
So if I were to do partial zeta, we'd get partial x1, we'd get 1. So we could sub that in. Partial x1 would be 1, and then.
Oh yeah, this is definitely wrong.
Which one? The board or?
On 87, I'll write it out. I should have.
Yeah, this.
I've not inverted. And if you double check like I think you're doing,
that gives you 1.
You don't get 1, do you?
No, they get you 3 minus 3n, and then let me go there. 3n, 2, give you that 1 term, and then jy with respect to partial y should give you j partial y. Yeah, you should get a 0 on the x1 term.
See, this is I have failed to invert v2 inverse. So like partial zeta, it's supposed to be what? It's supposed to be 1/2 v2 inverse partial y in my notation plus 1/2 because like y is x2. But v2 inverse, I should have like a j squared partial y plus j partial z times 1/2.
Jeez, okay. 1 sec, I'm checking something. Summation of j out of 1, x is partial zeta, xj partial zeta, and so you get partial x1, partial x plus, so you feed that through. Oh, this partial zeta. But don't you get the partial, this piece right here?
What's that? Which one?
When you feed it through, don't you get a 1 out of that first term before you plug in the v2, v3? I don't think you get 0 on that first term. That x, so when you take the partial zeta of the x term, because that x would go in there.
Oh, x doesn't give you anything. I mean, this, remember, this.
Because the second part I got also, but.
So this is, this is that, okay? So think about this hitting that. there's no x derivative. X, y, and z are independent.
Mm-hmm.
So like, there's no x derivative. This is just gone.
What is that term right there on your definition? The 3 minus n?
N is
Whatever.
3.
N is 3. Oh, gotcha.
So, but you see how this works? Is then like the j squared in the partial z
Yeah, I got that part
combines
from the
with-
summation, yeah.
combines with the j to give me j cubed,
Mhm.
and then get another j cubed here.
Yeah, but then you get the inverse, and then that's why the j squared's out in front.
Yeah. So I gotta fix this. That is.
Oh, okay, so
There's an error in my equation 87. I wonder if that propagates.
So your n term is how many dimensions you have?
Yeah, n is the
Dimensions?
dimension.
Okay. No, it's zero. And then,
Oh, look at this. So then, like for the last half of equation 87, all of a sudden I find my way. So I've got like partial x minus j squared partial y.
partial y plus j, partial z. Okay, yeah, and then this partial zeta equal to this 1/2 a squared j partial y partial 1 plus j b squared partial zeta equal 1. Wait, but no, nope, that's 2. 2 divided by, yep, okay. I was like, that's definitely 2. Then
So-
I forgot about the 1/2 off.
Now, when you look at the second two equations in 87,
Mm-hmm.
I've got it right? Like the
Yeah,
partial x minus j squared partial y. So j squared is
this is bar, V2 bar.
v2. So that's v2 inverse, which is j squared.
Mm-hmm.
And I've got the v3 inverse, which is
1.
which is which j squared's inverse is j.
Yeah.
So that's why I have that minus j there, partial z. So the conjugate derivatives are fine. I just have a typo. Let's be optimistic. A typo for the start of it. And when you go to the next page, we're on page 30.
We do partial x, which is equal to all these combined. Okay, so this is theorem 6.9 that you got the partial x is all these combined here. Let's go back to 6.9. Yeah, okay. You said that in 6.9 because of the BK theorem. So.
Oh yeah, this I haven't actually talked to you about this yet, and oh man, I'm missing some partials here, dude. Man, I'm missing some partials in this equation. I thought I'd fixed stuff like this in here before. Sometimes when you go back and look at something, all kinds of new wrong stuff. I mean, I'm missing some in that 6.9.
Mm-hmm.
See, I'm missing. Where did it go? If you look at
so you can
in the statement of theorem 6.9 itself, I'm missing some partials. That's what I'm trying to say. You see it?
I'm just working out. Wait 1 sec. So partial x is equal to.
Are you just going to add the partial? Check the claim.
Yeah. Partial y plus j squared. Oh wait, you can just pull out all those. So you get 1/2 partial y plus j squared partial z. No wait, no. This is the other way around. This is squared. This is 1. This is z. And then we add partial x minus j squared y partial y, and then you add partial x minus j partial x, no, partial z, so, and then that goes, no, yeah, and that goes, see, you got, is it supposed to equal out to 1? Is partial x supposed to equal 1?
Partial x, partial x?
Yeah, partial x.
Yeah, that's 1, yeah.
Okay. And then same thing for here, that you subtract. So when you subtract, you get, what you call this? J. Okay, so you get this one minus this one. So you get j, so you get this 2j squared. No, you don't. Wait, no. You get 2j squared. Forgot. 2j squared, and then you minus this, so that when you add this, that cancels out, and then that cancels out. So you get a j squared. Wait. I'm on partial y.
So like when you look at the sum of partial zeta bar 2 and partial zeta bar 3, what happens is the y and z partial derivatives cancel, because the one has plus, the other has minus. Like you've got 2 plus terms from the partial x. Just look at the board for a second. See these in partial zeta? You've got this and that, right?
Yeah.
But when you look at the definition of this and this, it's got partial x, right? But it also got minus this, and the other one's got partial x, but it also got minus that. So the z terms with j's, those cancel out, and all you're left with is like partial x plus partial x with the 2, which is that again.
Yeah, that's what I got for the partial x. I'm looking at partial y, where you get a plus j2.
Oh.
Yeah, I don't know. Okay, so when I'm looking at partial y, you have partial y. You pull it, so j, but when you put partial zeta in, that is j squared partial y plus j partial z minus zeta 2, which is partial x minus partial x plus j squared partial y.
Well, let's see here. This much I would say, like when we think about adding the difference of 2 and the 3 conjugate derivatives, that makes the x partial cancel. You have 1/2 partial x for both of them, so when you subtract the pair, you get rid of the x derivative.
I'm talking about the j squared term.
Right. So you only have, my point is, when you think about the partial y or partial z, you only need to think about y and z, because the x's cancel.
Yeah, x cancels. This is.
So you're thinking about the j.
Here, let me write it out.
Yeah, you just have to write it out, I think.
Yeah, I just write it out right here. This is what I'm looking at.
Oh, here. The green marker's miserable.
J2. So you get. Then you minus this zeta's 2, which is, but this is already minus, so it'd be plus j squared partial y. Unless I'm doing something wrong up here.
But the x term cancels, right?
Yeah.
So.
Yeah, the x term cancels with the next one because you just.
Okay, you're writing it out. Okay. Oh, I got you.
And then minus j partial z.
Now that's all times j squared, right? Over
So
time.
times j.
Well, that's all times j.
Yeah, so you
Oh, right. I'm sorry, my
So
bad.
you get left with the j squared term.
2's cancel, j times j squared, j cubed. Bingo. Got
Yeah, so what do you do with these two? You add them?
it. Uh-huh. So it gives you twice partial y, j squared times j.
Y is partial y, j squared times j.
You got a j out front, you got a j
Yeah.
squared next to both of them.
Yeah,
And
and then you get
there's
this.
still the j, so you have j.
Yeah. And then that'd be 1, which would give you partial y.
Mm-hmm.
Because, yeah, they're inverses of each other, right?
Yeah, well, and j cubed is 1, right? So,
Yeah.
and there's a half, and there's the
Yeah, the
half and
the
the 2. Yeah, yeah.
So you're supposed to get partial y?
Uh-huh.
But for partial zeta, you get 1. I don't know. That's crazy.
Equation 88 said that partial y is j times the sum of the derivative with respect to zeta minus the derivative with respect to zeta 2 plus the derivative with respect to zeta 3.
88.
88, yeah. You derived the middle equation in 88 just now, yeah.
And then j squared, yeah, that's going to do the same thing.
Mm-hmm.
And
Similar. So, now, equation 89, like I would not advocate deriving equation 89 from 88. Okay, you can, but, and if you, well, I mean, anyway, if you do, what I'm trying to get at here, Roderick, is that,
it's not that bad looking.
no, but what I'm trying to say is the motivation for why to do that is not apparent here. Okay? Like
Okay.
why, okay, great, partial x squared minus partial y partial z. Why look at that? Why not partial x squared minus partial x partial z or something else, you know?
Mm-hmm.
So I should explain why those derivatives are interesting, but setting that curiosity aside for the moment, the formulas are very interesting, right? Because if you look at the formulas in 89, do you notice something that pops out at you if you look at it? Every single term there has a conjugate derivative,
Yeah.
right? There's no naked, like just partial zeta squared or partial zeta.
Mm-hmm.
So what this means is that if you have a function which is h3 differentiable, meaning that the conjugate 2 and conjugate 3 derivatives vanish, it automatically solves these 3 partial differential equations of order 2. So these are the generalized Laplace equations for the 3 hyperbolic numbers. Or at least there's some of them.
But yeah, you just solve these by plugging back in, right?
Mm-hmm.
Yeah.
Oh, yeah. But anyway, there are better ways to think about generalized Laplace equations. Okay.
Yeah.
Want a drink?
I'm good. Better now.
Okay. I think I need to get coffee. Let's see here. All right. Well, I have majored in the minors. So now I need to go back to. Oh, okay. So the point of all this was to explain example 5.6.
5.6. 5.6. Let an algebra dimension 2 or greater than 2 with invertible basis. So what we just did, didn't it?
Mm-hmm. Now notice the function, I'm defining a function,
Yeah.
f of zeta equals to zeta bar 2.
Yeah.
That function is available to define in any algebra of 2 dimensions or higher
Yeah.
with an invertible. Well, there is always an invertible basis, that's another theorem.
Yeah.
So that function, f of zeta equals zeta bar 2, has partial f partial zeta bar 2 equal to 1, which is not equal to 0.
Mm-hmm.
Therefore, that is an example of a non-a-differentiable function in any algebra of dimension 2 or higher. So it's just a very general counterexample. Like if you want to find a function which is not differentiable with respect to the algebra, if you know about the conjugate variables, a simple choice is just f of zeta equal to zeta bar 2. So, for example, in complex analysis, an example which is often given is if you want to find a function which is not complex differentiable, f of z equal to z bar, it's like the standard example.
Okay.
Because it doesn't satisfy the Cauchy-Riemann equations. There are other examples, of course, but this is just a greedy uber example, and also an excuse to point readers to my future section.
It is differentiable, just not on the algebra.
That's right. It is a real differentiable function for sure, because it's just a linear. It is linear in the Cartesian variables.
Yeah.
Right. All of its partial derivatives are constant. It's a
Yeah.
smooth function. It's just not a differentiable. Okay. So now in the next paragraph, I talk about what I mean for a function to be a-differentiable on an open subset. Right.
Mm-hmm.
And so if it's a-differentiable at each point in V, then we say it's a-differentiable on V. And if there exists an open set containing P on which A is differentiable, then we say it's a-differentiable near P, and we write F as an element of CAP. So, and as I say, there are several ways to characterize a-differentiable at a point. These all follow from the isomorphism that the algebra is isomorphic to the right A-linear maps,
Which is the matrix.
which is isomorphic to the matrix the matrix representation of A with respect to the basis beta. So, so there's the theorem 5.7. So number 1 is just literally, a differential. That's literally just right linearity of the differential, right? So if you assume that the function is R differentiable, in other words, so that means that to assume it's R differentiable is to assume that there exists a differential that satisfies this difference quotient, right?
Yep.
So if you know in addition that the differential is right alinear, that makes it a-differentiable. So there's the following are equivalent, right?
Yeah.
Let's see if we can prove that. So what is 2 saying? It's saying that you can.
There exists a lambda for the algebra for which d of p of v, the differential of v, is equal to lambda star v.
Right.
For every v. But didn't we prove that, or didn't we see that with another thing? That with the vk thing?
The VK thing?
Yeah, that like we said the df of xj is equal to the df of v vj times I have it, sorry, one second. Yeah, the differential, the partial f partial xk is equal to the derivative at p of f on bk. Isn't that what that is saying? Just replacing bk with lambda?
Let's see, so you're saying the partial, what was it, partial f?
Partial f partial xk
Uh-huh.
is equal to dpf bk.
Right.
And this is saying there exists a lambda in the algebra for which dpf v is equal to lambda star v.
dpf. So v is not necessarily a basis element, right?
No, it didn't say that it's a basis element.
So, but this, of course, we could write as dpf of 1 times v, right?
Yeah.
Which then, if we're assuming right differentiability,
Yeah, no, it says let it be a right, R, or no, real differentiable, no, I'm sorry. It says real differential, it didn't say right.
well, the claim is that those are equivalent, right? So we've got 1, we've got
Yeah.
2, we've got 3, right?
Mm-hmm.
So how are you going to prove those are equivalent? You could do 1 implies 2.
Yeah.
You could do 2 implies 1. I'm not sure.
Oh yeah, one, if you have one says it's right. One states that it's right differentiable.
Yeah, so I'll tell you, I'm going to do 1, I'm going to ignore the proof and just
Yeah.
do 1 implies 2.
Yeah.
So suppose that 1 is right different, right a different,
Yeah.
right? So 1 says that we can pull v out, right?
Mm-hmm. And then the subnote here says it's commutative. But you don't really need it for commutivity. You don't need commutivity.
Right. So
And so you're saying DPF it would be is a something
we could just call this
lambda.
lambda.
Yeah. Yeah, that's what I was saying.
Another way to say this is that dpfv is a left multiplication map.
Yes.
It's left multiplication by lambda. It's left multiplication by what though? It's left multiplication by the differential
The identity.
at the identity. Yeah. So that's 1 implies 2. 2 implies 1. 2 implies 1 we talked about before, right? So 2 implies 1
Well, yeah, because you can't do it if it's not differentiable, right?
is
It'd be if and only if.
well, 2 implies 1. dpfv is equal to lambda times v, right?
Mm-hmm.
So that's L alpha L lambda of v in our previous notation,
Yeah.
right? But we discussed this previously that left multiplication by lambda is a right linear map.
Yes.
Of course, like I'm being stupid, it's just as easy to just prove right linearity directly, right? Like it
Yeah.
is literally this much writing. Which is exactly the calculation we did to prove that left multiplication maps were right linear. It was critical middle step there, of course, is associativity. So this proves that 1,
And 2 are an if and only if statement.
yeah.
And then we proved that without basis either too. Like we don't need a basis.
Yeah, there's no no basis involved here. And then like 3 for any basis beta of A, the matrix of the differential with respect to the basis beta is an element of the regular representation of A with respect to the basis beta. Goodness, I think that's essentially just the definition. The fact that that's true is essentially just the definition of the regular representation with respect to a basis, because we define M to be beta to be the set of matrices that are the set of matrices of right linear maps.
Yeah.
So
And then 3 is for any basis beta of A. differential of point at point P of F.
Okay.
The beta basis
Right.
is MA beta.
No, I was. So I was saying that the A number lambda, which appears in this theorem, is known as the derivative of f at P. All right. That was a concept. So for any differentiable function with dpf of v equal to lambda times v, we say lambda is the derivative of f at p. But can you, I mean, we can be a little bit more sort of explicit about this. So, that, I mean, definition, f prime of p is equal to dpf of 1. And moreover, like dfp of v, right? Well, we know the usual song and dance. I'll go through it again. dpf of 1 times v, right? Which is dpf of 1 times v. Of course, this is what we called lambda a second ago, but I'm giving it a new name. It's f prime of p times v.
Well, if it's a point, then you just go away.
So let's see here. Let me try to explain to you why this is so kind of exciting. So if I have a function, say from R3 to R3, right? And you have something like f of x, yz is x squared, y squared plus z squared, x squared minus x, yz, whatever, right? The differential, what's the differential of this look like? Well, the differential of f at some point p, right? Acting on, let's say, you know, h1, h2, h3, it's equal to, well, Jacobian of f at the point p times, you know.
So it's just the Jacobian would be the first, everything hit by the partial x, everything hit by partial y, then everything hit by partial z, all split up, right?
Exactly. So it's like, you know,
2x, 0, 0, no, 2x, 2x, yeah, and then 0, 2y, y, minus y, no, minus z, sorry, and then 0, 2z, y, minus y. Yes, minus 1. And then I'll have by h1, h2, h3.
right. So, all right, let me point out here.
We have a matrix representation of any at any point in the algebra. Oh no, sorry, right here. Sorry.
Right. So this is just a, you know, plain old function on R3. This is Jacobian matrix, which is, I mean, if you read Edwards' Advanced Calculus, for example, he would call that, or the linear operator to which that matrix corresponds, the differential. He actually calls No, I think he actually calls that Jacobian matrix the derivative, if I remember right. I think for him the derivative is the matrix of the differential. Right? So the function and its derivative, even at a point, like at a point, the function gives you a vector. At a point, the derivative gives you a matrix, right? If we think about this, not just if we don't freeze the point, we think about the, this sends vector to vector, right? This would send vector to matrix. So you trade a vector valued function for a matrix valued function. In other words, the derivative is really not an object of the same type. So for an arbitrary real differentiable function, the kth derivative is naturally associated with a k-symmetric tensor because you have partial derivatives commute.
Yeah.
So you can chop it down to look at it as a k-symmetric tensor. Now, you haven't thought about this much because you haven't really thought about what is the derivative of a function from Rn to Rn, right?
No.
This has been hidden in your education thus far because we look at functions that are from like R to R, right? And in that case, the analog of the Jacobian matrix is a number. So you can still like identify the number with the matrix in some sense, you know? Or when you're looking at functions from Rn to R, the derivative is essentially taken care of by the gradient vector. And it's just still kind of a little bit hidden from you. But this idea that the derivative is well, you start to see it in calculus 3. You start to see in calculus 3, if you really were paying attention, that for a function of more than one variable, the derivative is not again a function. It's like there's this gradient vector.
Yeah.
Yeah. So over here, for an adifferentiable function, I'm telling you that we can still define the derivative
Through the Jacobian.
Not the Jacobian.
But the tensor?
No. Look. So the differential is given by multiplication by f prime of p, that specific number, which is dpf of 1. In other words, definition, you can say f prime is, again, a function from the algebra to the algebra, where what?
This holds over here.
Where f prime of p is just equal to dpf of 1. For all such p in the domain of f, you could make this just not, you could make this for like, for all points for which the function's a differential. I mean, just like we do regularly, if we have a derivative, we have a function, we define the derivative for usually a smaller set in principle and so forth. That could also be done here. But my point to you is that the derivative is again a function on the algebra, even though this could be R3. Why is that possible? Because I just got done showing you the Jacobian matrix, right? But what does the Jacobian matrix for a differentiable function look like? Right?
Not the same.
Right. If
we had a function alpha, it would just be partial.
Yeah. Let's easy case, right? Easy case. So suppose that the identity is the just for the moment, for the sake of not getting into the basis dependent so much, let's assume that the first basis element is the identity, right? In that case, the dpf1 is the first thing, right? So f prime of p is the first column.
Yeah.
And then you'd have like f prime of p times v2.
Yep.
F prime of p times vn. Yeah. So, I mean, yeah, you could still write the differential in terms of the, Jacobian matrix times your vector. But you could also just write it as that value, that A number. Because the thing is, the Jacobian matrix, it only appears to be a matrix. Actually, that matrix is fixed by a particular value in the algebra, just in one column.
Yeah, but we don't, because you would just pull f prime out of p, right?
You know,
Because f prime of p should give you something you can pull out, because it's in every term.
I don't know, I hadn't thought about this, but fine, let's multiply this by h. I guess you could say I'm doing this with respect to the basis beta. Like this is, let's say that this is, oh, I'm really getting into the weeds here. dpf of v equal to this, where v is equal to like, you know, h1 plus h2 v2 hnvn. Because if you feed that v into the differential, then you get like, well, you can write it as this matrix product because of the well, Cauchy-Riemann equations, of course, but let me just write this out for a second here. So this is equal to, you know, h1. Oh. I really don't want to write that out. Oh, I think to make sense of like this, we're going to have to get down into the structure constants. Let me not do this. I don't think that's productive. Let's see here. How can I explain this? I mean, this is essentially it. That.
All I was trying to say is
Mhm.
that f prime of p creates a value that everything has. So you would just have, you could make the Jacobian a matrix of f prime of p times the identity, and then everything times the identity to b2 to b1, and then which would give you v in your case, which would be f star p times b, like matrix wise too. Once you convert it back over, pull the f prime p, and then you get the identity.
Pull it out.
Yeah.
Oh. I don't know if I can do that. F prime of p is not a number. I mean, it's an A number.
Yeah. But I mean, that's just a distributive. And even if it's right at linear, you can still do that, I'm pretty sure.
For example, it could be this: A, B, C, C, A, B, B, C, A for H3.
Mm-hmm.
So like this could, you know, this would be F prime. This is, I'm going to drop the P, F prime J. This is, you know, F prime J squared.
Okay. Okay.
And, you know, if I multiply that by H1, H2, H3.
Yeah, you get f prime h1, f prime j h2, f prime j squared h3.
Tell you what, I'll look at this one for a second. H1,